Close your eyes and consider this. In 1854, a young German mathematician stood up in a university lecture hall in Göttingen and described a new kind of geometry, a geometry in which space could curve, in which the rules that Euclid had laid down 2,000 years before, the rules that had governed mathematics ever since, simply did not apply. The professors in the room sat in silence. Some were confused, some were skeptical. None of them understood, in that moment, what they had just heard. They could not have known that this anxious, frequently ill young man was describing the shape of the universe itself. 60 years later, a Swiss patent clerk in Bern sat at his desk and realized that the mathematics he needed to describe his theory of gravity, mathematics that would explain how space and time themselves were shaped by matter and energy, had already been invented by a man who had been dead for half a century, by a man who had described it not because he knew the universe was shaped that way, but simply because he was curious about what geometry could be in its purest and most abstract form. The mathematician's name was Bernhard Riemann. The patent clerk's name was Albert Einstein. And the story of how one man's pure mathematical imagination became the other man's description of reality across 60 years of silence is one of the most extraordinary stories in the history of human thought. Tonight, we are going to follow that story from beginning to end, slowly, the way a story this deep deserves to be told. We are going to meet Riemann in his world of 19th century German mathematics, brilliant and isolated and dying young. We are going to watch him invent a mathematics so revolutionary that no one in his lifetime understood what he had done. We are going to follow that mathematics through 60 years of silence, studied by a few specialists, ignored by everyone else, waiting in libraries and journals for someone who needed it. And then we are going to watch Einstein discover it, recognize it, and use it to write the equations that describe the curvature of spacetime itself. This is not just a story about two brilliant men. This is a story about the relationship between pure thought and physical reality, about ideas that arrive before their moment and wait, sometimes for decades, sometimes for centuries, for the mind that will recognize their truth, about the mysterious fact that mathematics, developed entirely in the human imagination, keeps turning out to describe the actual structure of the universe with precision that borders on the miraculous. Lie back and let this mystery settle into you, the way the best questions do, not to be solved quickly, but to be lived with, contemplated, turned over in the mind like a smooth stone. George Friedrich Bernhard Riemann was born in 1826 in the small village of Breselins in the Kingdom of Hanover, in what would later become northern Germany. His father, Friedrich Bernhard Riemann, was a Lutheran pastor, educated but poor, struggling to support a family of 8 on a pastor's modest income. Bernhard, as he was called, was the second of 6 children, a shy, anxious boy who from his earliest years showed an almost supernatural facility with numbers and patterns. The village schoolmaster, recognizing something extraordinary in this quiet child, gave him advanced mathematics textbooks that were far beyond the level of his classmates. Days later, he would return to find that Bernhard had not only read the entire book, but had mastered its contents completely, often finding shortcuts and connections that the textbook authors had missed. The boy's mathematical gifts were evident to everyone who encountered him, but so was his profound social anxiety. He struggled to speak in public, a difficulty that would plague him throughout his short life and present enormous challenges for someone who would need to lecture to earn his living. He was deeply religious, like his father, and initially planned to following his father's footsteps and become a pastor. But the pull of mathematics was too strong, and with his father's reluctant permission, he shifted his focus to the subject that seemed to live more naturally in his mind than language itself. In 1846, at the age of 19, Riemann arrived at the University of Göttingen to study mathematics. Göttingen was the greatest mathematics department in the world at that time, home to Carl Friedrich Gauss, the most celebrated mathematician of the age, sometimes called the Prince of Mathematics. Gauss was a towering figure whose work spanned number theory, astronomy, physics, and geometry with a depth and breadth that had not been seen since Newton. He was also famously difficult, brilliant, demanding, impatient with minds that could not keep pace with his own. For most students, studying under Gauss was an intimidating and often humiliating experience. But Riemann was not most students. Gauss recognized immediately that this shy, awkward young man possessed a mathematical mind of extraordinary power, the sigh of hopeless spirit, Gauss evil to expanded Christianity. Riemann could follow the most abstract mathematical arguments with an intuitive ease that impressed even Gauss, and more remarkably, he could extend those arguments into territories that no one had explored before. Under Gauss's guidance, Riemann began to develop the mathematical ideas that would define his legacy, working in the quiet intensity that was natural to him, pursuing questions that seemed to have no practical application, but possessed a pure logical beauty that drew him forward. The relationship between Gauss and Riemann was one of the great teacher-student partnerships in the history of mathematics. Gauss, in his 70s, had spent decades thinking about the deepest problems in mathematics and physics. Riemann, barely past 20, brought to those same problems a fresh perspective and a willingness to question assumptions that even Gauss had taken for granted. Together, they pushed into mathematical territory that would not be fully explored for decades after both men were dead. But Riemann's health was fragile from the beginning. He suffered from what his contemporaries described as nervous collapse, episodes of profound anxiety and depression that would leave him bedridden for weeks at a time. His constitution was weak, his body thin, and frequently racked by illness. He lived in a constant state of financial worry, as his family could provide little support, and academic positions were scarce and poorly paid. Through all of this, he continued his mathematical work with a quiet persistence that bordered on the heroic. In the German university system of the 19th century, before a scholar could become a professor, he had to deliver what was called a habilitation lecture, a public demonstration of his qualifications to teach at the university level. Riemann prepared 3 possible topics and submitted them to Gauss, fully expecting that Gauss would choose the first 2, which were in areas where Riemann had already done extensive work. Instead, Gauss chose the 3rd topic, the foundations of geometry. It was the one Riemann had prepared least, and it sent him into months of intense, often agonizing work. The subject Gauss had chosen forced Riemann to think about the most fundamental questions in mathematics. What is geometry? What is space? Are the rules that Euclid had laid down the only possible rules? Or could there be other kinds of geometry, other ways of organizing space? These questions had occurred to mathematicians before, but no one had pursued them with the systematic thoroughness that Riemann brought to the task. Working through illness and exhaustion, often barely able to rise from his bed, Riemann constructed a new understanding of geometry that was so revolutionary, it would take the rest of the mathematical world decades to catch up. The lecture he delivered on June 10, 1854, in a small hall at the University of Göttingen, was titled "On the Hypotheses Which Lie at the Foundations of Geometry." The audience consisted of a handful of professors and graduate students, most of whom expected a routine academic presentation on a technical mathematical topic. What they got instead was one of the most profound revolutions in mathematical thought ever delivered in a single hour. Riemann, speaking quietly and with obvious nervousness, described a universe of geometric possibilities that no one in that room had ever imagined. For 2,000 years, geometry had meant Euclid's geometry, flat space, parallel lines that never meet, triangles whose angles always add up to exactly 180 degrees. The shortest distance between 2 points is a straight line. This geometry described the world of human experience perfectly, the geometry of carpenters and architects and surveyors, the geometry of everyday life. It felt not just useful, but true, not just convenient, but necessary. It seemed to describe the fundamental structure of space itself, as fixed and absolute as the laws of logic. But Riemann asked a simple question. What if it isn't? What if the geometry we experience in our daily lives is just one possibility among many? What if space could be curved in ways we had never imagined? What if the rules of geometry were not absolute truths, but descriptions of particular kinds of space, descriptions that might or might not apply to the space we actually inhabit? To understand what Riemann was proposing, imagine that you are a two-dimensional being living on the surface of a sphere, like an ant crawling on a basketball. From your perspective, the surface you inhabit feels flat. You have no awareness of the third dimension in which the sphere is curved. But if you were to draw a triangle on this spherical surface, measuring carefully with the best instruments available to you, you would discover something strange. The angles of your triangle add up to more than 180 degrees. The amount by which they exceed 180 degrees depends on how large the triangle is. Larger triangles have angles that deviate more from the Euclidean prediction. You might initially assume that your instruments are flawed or your measurements are imprecise, but as you repeated the measurement with increasing care, using larger and larger triangles, the deviation would become more and more apparent. Eventually, you would be forced to conclude that you do not live in Euclidean space at all. You live in a curved space, a space where the familiar rules of flat geometry simply do not apply. The curvature is built into the space itself, not into the objects within it. This is spherical geometry, one of the non-Euclidean geometries that mathematicians like Gauss, Bolyai, and Lobachevsky had discovered in the early decades of the 19th century. On the surface of a sphere, parallel lines do not exist in the Euclidean sense. The lines of longitude on a globe, for instance, are all parallel to each other at the equator, but they meet at the north and south poles. The shortest path between 2 points on a sphere is not a straight line, but the arc of a great circle, the kind of path that airplanes follow when they fly long distances across the Earth. But Riemann went far beyond these particular examples of curved geometry. He asked the most general possible question: what is geometry at its most fundamental level? His answer was revolutionary in its simplicity and its implications. Geometry, Riemann argued, is the study of how to measure distances in a space. Given a rule for measuring distances between nearby points, what mathematicians call a metric, you can determine everything else about the geometry of that space. The curvature, the behavior of parallel lines, the sum of the angles in triangles, all of this follows from the metric. And there is no reason, Riemann realized, why space must have a fixed, uniform metric. Space could curve differently from place to place. The curvature could vary smoothly across the space, like hills and valleys in a landscape. The space could have any number of dimensions, not just the 3 dimensions of everyday experience, but 4, 5, or any finite number. The geometry of space is not given to us in advance by some absolute mathematical necessity. It is a property of the space itself, something that can be measured and described, and that might be different in different regions or different universes. To express these ideas mathematically, Riemann invented what is now called the Riemann metric tensor. A tensor is a generalization of familiar mathematical objects, like numbers and vectors, a way of organizing information that transforms in predictable ways when you change your point of view. The metric tensor contains, at each point in space, all the information needed to measure distances and angles in every direction. It is a mathematical object that can describe the geometry of any curved space in any number of dimensions with complete generality. The metric tensor is not easy to visualize. It lives in the abstract realm of mathematical formalism, but its implications are profound. It means that any conceivable geometry, no matter how curved or complex, can be described with mathematical precision. It means that the question of what kind of space we actually inhabit becomes an empirical question, something to be determined by measurement and experiment, not by philosophical argument or mathematical assumption. When Riemann finished his lecture and sat down, the room was silent. Most of the audience had understood little of what he had said. The mathematics was too advanced, the concepts too foreign to their way of thinking about space and geometry. But Gauss understood. At 77 years old, in poor health and rarely impressed by anything, Gauss spoke to colleagues afterward about Riemann's ideas with what those colleagues described as unusual warmth and enthusiasm. Gauss had spent decades thinking about the geometry of curved surfaces, particularly about how to measure distances and angles on the surface of the Earth, for his work in geodesy and map-making. He recognized immediately what Riemann had accomplished. Riemann had not just extended Gauss's ideas about curved surfaces. He had generalized them to spaces of any number of dimensions, and had shown that geometry itself, the ent maybe calm, the space was far more flexible and mysterious. Gauss recognized that this shy, sickly young man had gone further in a single lecture than the entire mathematical community had gone in centuries of thinking about the nature of space. It was the last great mathematical insight of Gauss's life. He died the following year, in 1855, having witnessed the birth of a completely new understanding of geometry. Riemann's health continued to deteriorate. The nervous strain of preparing and delivering the habilitation lecture had exhausted him, and he spent months recovering from what his doctors called nervous fever. But the lecture had achieved its purpose. He was granted the right to teach at Göttingen, though the position came with no salary and little prospect of financial security. He continued his mathematical work, developing the ideas from his lecture into a comprehensive theory of curved spaces, but his body was failing him. In 1866, seeking relief from the harsh German winters that aggravated his tuberculosis, Riemann traveled to Italy. He settled in a villa overlooking Lake Maggiore, hoping that the warm climate would restore his health. But it was too late. On July 20th, 1866, at the age of 39, He died on a hillside under a fig tree, his wife Elise holding his hand as he looked out over the lake. His last words, according to those who were with him, were about the beauty of the mathematical structures he had spent his life exploring. He died as he had lived, quietly, intensely focused on ideas that seemed to exist in a realm beyond the physical world. Riemann left behind a body of mathematical work that was breathtaking in its depth and originality, but also frustrating in its incompleteness. Many of his ideas existed only in fragments, notes and sketches that hinted at profound insights without developing them fully. His friend and colleague Richard Dedekind spent years after Riemann's death editing and publishing his mathematical papers, trying to reconstruct the full scope of his vision from the materials he had left behind. What emerged from this careful scholarship was the recognition that Riemann had single-handedly created an entirely new branch of mathematics, differential geometry, the study of curved spaces of arbitrary dimension. His metric tensor became the foundation for everything that followed. Mathematicians built upon his ideas extensively throughout the late 19th and early 20th centuries, developing a rich and sophisticated theory of curved spaces that was admired for its abstract beauty and logical elegance. But for 60 years, this mathematics remained purely abstract, a magnificent intellectual edifice with no apparent connection to the physical world. Riemann's geometry was studied and extended by specialists who appreciated its mathematical depth, but it seemed to have no practical application. It was mathematics for its own sake, pursued out of pure intellectual curiosity, with no expectation that it would ever be needed to describe anything real. During those 60 years, the physical sciences were undergoing their own revolution, though it was not immediately apparent how that revolution would connect to Riemann's abstract geometry. Newton's mechanics, which had governed physics for 200 years, seemed unassailable. It described the motion of planets and projectiles, the behavior of gases and liquids, the swinging of pendulums and the orbiting of moons with extraordinary precision. The Newtonian picture of the universe was one of absolute space and absolute time, a fixed stage on which physical events played out according to deterministic laws. But in the second half of the 19th century, small cracks began to appear in this seemingly perfect edifice. The orbit of Mercury, the innermost planet, did not quite match Newton's predictions. Its perihelion, the point in its orbit closest to the Sun, shifted slightly more with each orbit than Newton's theory predicted. The discrepancy was tiny, only 43 arc-seconds per century, but it was real and persistent and completely unexplained. Astronomers proposed various explanations. Perhaps there was an undiscovered planet inside Mercury's orbit, or perhaps Mercury was not perfectly spherical, but none of these explanations survived careful observation. Meanwhile, James Clerk Maxwell was working out the mathematics of electricity and magnetism, unifying these phenomena into a single theory of electromagnetism. Maxwell's equations, published in their final form in 1865, showed that electric and magnetic fields were different aspects of a single electromagnetic field, and that disturbances in this field propagated as waves at a speed that Maxwell calculated to be exactly the speed of light. Light itself, Maxwell realized, was an electromagnetic wave. But Maxwell's theory created a new puzzle. The speed of light, according to his equations, was a fixed constant, approximately 300,000 kilometers per second. But fixed relative to what? In Newton's universe, all velocities were relative. The speed of a train depended on whether you measured it from the ground or from another train. If light moved at a fixed speed, that speed had to be relative to some absolute reference frame. Maxwell and his contemporaries assumed that this reference frame was the luminiferous ether, a mysterious substance that filled all of space and served as the medium through which light waves propagated. The search for the ether became one of the great experimental challenges of the late 19th century. If the Earth moved through this stationary ether, there should be an ether wind that affected the speed of light in different directions. The most famous attempt to detect this wind was the Michelson-Morley experiment of 1887, which used an ingenious interferometer to measure the speed of light in perpendicular directions with unprecedented precision. The result was completely unexpected. No ether wind was detected. Light traveled at the same speed in all directions, regardless of the Earth's motion through space. This null result was deeply puzzling. Either the Earth was stationary relative to the ether, which seemed inconsistent with the Earth's orbital motion around the Sun, or the ether did not exist at all. Various explanations were proposed, including the idea that objects contracted in the direction of their motion through the ether, but none of these explanations was entirely satisfactory. The problem of the ether remained one of the great unsolved mysteries in physics as the 19th century drew to a close. Into this intellectual ferment stepped Albert Einstein, a young man whose mind worked in ways that would prove perfectly suited to the puzzle of reconciling Maxwell's electromagnetism with the principles of relativity. Einstein was born in 1879 in Ulm, Germany, 14 years after Maxwell's equations were published and 13 years after Riemann's death. He grew up in a world where the problems of physics were becoming increasingly mathematical and increasingly abstract. Einstein's path to revolutionizing physics was not straightforward. He was a good but not exceptional student, more interested in thinking about fundamental questions than in memorizing facts or solving routine problems. After graduating from the Federal Polytechnic in Zurich in 1900, he struggled to find an academic position and ended up working as a patent examiner in the Swiss Patent Office in Bern. It was there, in 1905, while evaluating patent applications during the day and thinking about physics in his spare time, that he produced 4 papers that changed the course of science. The most famous of these papers introduced special relativity, Einstein's solution to the puzzle of the ether. Einstein proposed 2 simple postulates. First, that the laws of physics are the same in all inertial reference frames. And second, that the speed of light is constant for all observers, regardless of their motion. These postulates seemed innocent enough, but their implications were revolutionary. If the speed of light is truly constant for all observers, then space and time cannot be absolute, as Newton had assumed. Instead, they must be relative. Observers in relative motion will measure different distances and different time intervals for the same events. Space contracts and time dilates in ways that ensure the speed of light remains constant. Mass and energy become interchangeable, according to the famous equation E equals mc squared. The ether disappears entirely, is not needed because light requires no medium through which to propagate. Special relativity was a stunning achievement that resolved the contradictions between Maxwell's electromagnetism and the principles of physics. But even as Einstein was celebrated for this breakthrough, he was already aware of its limitations. Special relativity described flat spacetime. It treated space and time as a unified 4-dimensional continuum, but it assumed that this spacetime had the flat geometry of Euclid. And special relativity said nothing about gravity, one of the fundamental forces of nature. Einstein spent the next 10 years trying to incorporate gravity into relativity. and those 10 years were among the most intellectually challenging of his life. The problem was not just conceptual but mathematical. The mathematics he needed to describe curved spacetime in 4 dimensions was far beyond anything he had learned as a student. He needed help, and he turned to his oldest and most trusted friend from their student days in Zurich, Marcel Grossmann. Grossmann was a mathematician who had specialized in the differential geometry that had grown out of Riemann's work. When Einstein wrote to him in 1912, saying, "You must help me or I will go crazy," Grossmann responded by searching the mathematical literature for tools that might be useful for Einstein's project. Boccassuna. What he found was the absolute differential calculus, developed by Gregorio Ricci and Tullio Levi-Civita in the 1890s, based directly on Riemann's metric tensor and his understanding of curved spaces. When Grossmann showed Einstein these mathematical tools, Einstein felt simultaneously elated and intimidated. Here was exactly the mathematics he needed, a complete framework for describing curved spaces of arbitrary dimension, with all the tools necessary for calculating distances, angles, and curvatures. But it was also mathematics of extraordinary complexity and abstraction. Einstein later described his efforts to master it as the hardest intellectual work of his life. Einstein and Grossmann worked together for 3 years, publishing preliminary papers in 1913 and 1914 that outlined their approach but failed to achieve the opposite theory Einstein was seeking. The mathematics was so complex that Einstein repeatedly made errors, and several times he convinced himself that the approach was fundamentally flawed. He later described this period as one of the most difficult and humiliating of his scientific career. A man who had revolutionized physics with special relativity, struggling for years with mathematical concepts that pushed him to the limit of his craft abilities. The breakthrough came in November 1915. Working alone in Berlin, where he had moved to take up a research position at the Prussian Academy of Sciences, Einstein finally assembled the pieces of the puzzle. In 4 consecutive weekly lectures to the Academy, he presented the final, correct form of what he called the general theory of relativity. The field equations, 10 coupled nonlinear partial differential equations relating the curvature of spacetime to the distribution of mass and energy, with a culmination of 10 years of struggle. On the same day he presented the 4th and final lecture, Einstein used his new theory to calculate the precession of Mercury's orbit. Newton's theory had predicted that Mercury's perihelion should advance by 532 arcseconds per century due to the gravitational influence of the other planets. The observed value was 575 arcseconds per century, a discrepancy of 43 arcseconds that had puzzled astronomers for decades. Einstein's calculation gave exactly 43 arcseconds. The agreement was perfect. Einstein was so excited by this result that he told a friend his heart had pounded with excitement for several days. Here was definitive proof that his theory was not just mathematically beautiful, but physically correct. His ability was not to be real. The equations he had written using Riemann's metric tensor described the actual behavior of the universe with precision that exceeded Newton's theory. Riemann's abstract geometry had turned out to be the geometry of space-time itself. What the equations of general relativity say, in the simplest possible terms, is this: mass and energy tell space-time how to curve, and curved space-time tells matter how to move. What Newton had described as the force of gravity is, in Einstein's theory, the curvature of space-time itself. Objects in free fall are not being pulled by a force, they are following the straightest possible paths through a curved geometry. A planet orbiting the Sun is like a marble rolling along a curved surface, following the path that is straight from its own perspective, but appears curved to an outside observer. The Earth creates a depression in space-time around it, like a heavy ball placed on a stretched rubber sheet. Objects near the Earth, falling apples, orbiting satellites, the Moon itself, follow the geometry of this depression. The Moon is not held in orbit by a mysterious force reaching across empty space. It is simply following the straightest possible path through the curved space-time around the Earth. Time itself runs more slowly in the presence of massive objects, and light bends when it passes through regions of curved space-time. The confirmation of Einstein's theory came 4 years later, during the solar eclipse of May 29, 1919. Arthur Eddington led expeditions to Brazil and the island of Principe, off the coast of West Africa, to photograph stars near the Sun during the eclipse. Einstein's theory predicted that the Sun's gravitational field should bend the light from these stars, making them appear slightly displaced from their normal positions. Newton's theory also predicted a deflection, but only half as large as Einstein's prediction. The measurements were difficult and the results initially uncertain, but when the data was finally analyzed, it confirmed Einstein's prediction. The light from distant stars was indeed bent by the Sun's gravitational field, and by exactly the amount that general relativity predicted. The announcement of this result made Einstein famous around the world overnight. Newspapers hailed him as the man who had overthrown Newton and revealed the true nature of space and time. But the deeper significance was this: Riemann's geometry, developed 61 years earlier as an exercise in pure mathematical imagination, had turned out to be the exact language needed to describe the structure of the universe. Einstein had opened Riemann's papers and found that the abstract geometry of a dead mathematician was precisely the tool he needed to write the equations of gravity. Riemann had described the shape of the universe without knowing that the universe needed describing. This moment, Einstein reading Riemann's work and recognizing the universe within it, represents something profound about the relationship between mathematical thought and physical reality. Riemann had not observed curved space. He had not measured it, or detected it, or found evidence for it in any experiment. He had simply asked what kinds of geometry were mathematically possible, and followed the logic wherever it led. And the place it led was the actual structure of space-time. The story of Riemann and Einstein is not unique in the history of science. Again and again, mathematical structures developed for purely abstract reasons have turned out to describe aspects of the physical world that were only discovered decades or centuries later. Maxwell's equations were written before radio waves were discovered. Boolean algebra was developed as pure logic before anyone imagined it would become the foundation of computer science. The mathematics of complex numbers was explored for centuries before it turned out to be essential for quantum mechanics. What this suggests is something mysterious about the relationship between the human mind and the universe it inhabits. Why should mathematical structures that we create through pure thought correspond to physical structures that exist independently of our minds? Eugene Wigger called this the unreasonable effectiveness of mathematics in the natural sciences. And it remains one of the deepest puzzles in philosophy. Mathematics seems to capture something. By this time, the terrible capture is unconscious, but we do not understand why. Perhaps the most remarkable aspect of Riemann's story is that he never knew his work would be used to describe the actual universe. He died thinking of himself as a pure mathematician, someone whose work had no connection to the physical world. He pursued the questions that interested him. What is geometry? What kinds of spaces are possible? Without any expectation that the answers would matter to anyone but other mathematicians. He was motivated by curiosity alone, by the intrinsic beauty of mathematical structures, and the satisfaction of following an idea to its logical conclusion. And yet his work turned out to be essential for understanding the most fundamental aspects of physical reality. The equations that govern the expansion of the universe, the formation of black holes, the propagation of gravitational waves, the behavior of matter and energy on the largest scales, all of them are written in the mathematical language that Riemann invented. Every GPS satellite orbiting the Earth, every telescope observing distant galaxies, every detector searching for gravitational waves, relies on calculations that use Riemann's metric tensor. The space you are lying in right now is not the flat, absolute space of Newton's imagination. It is Riemannian space, curved by every mass in it, from the electrons in your body to the supermassive black hole at the center of the Milky Way. The curvature is mostly tiny, imperceptible in everyday experience, but it is real and measurable with sensitive instruments. The GPS on your phone has to account for the curvature of space-time around the Earth to give you accurate directions. The ground beneath you warps space by a minute but calculable amount. Your own body, simply by having mass, curves the space-time around it. This is the universe that Riemann described in that lecture hall in Göttingen in 1854. He had no way of knowing that his abstract mathematical constructions corresponded to anything real. He was simply exploring the space of logical possibilities, following mathematical ideas wherever they led, building structures that seemed beautiful and elegant from a purely intellectual perspective. The idea that these structures might describe the actual shape of actual space would have seemed absurd to him. But ideas have their own existence, independent of the minds that create them. Once Riemann had laid out the mathematical framework for describing curved spaces of arbitrary dimension. That framework existed as a permanent part of human knowledge. It sat in journals and textbooks, waiting for someone who needed it. For 60 years, it was studied by mathematicians who admired its abstract beauty without suspecting its physical significance. And then Einstein needed exactly that mathematics to write his theory of gravity, and Grossman was able to reach into the mathematical literature and hand it to him, complete and ready to use. There is something almost magical about this process. The way mathematical ideas developed for their own sake turn out to illuminate the structure of reality. It suggests that the universe itself might be, in some deep sense, mathematical. Not that mathematics describes the universe, but that mathematics is the universe. That the abstract structures we discover through pure thought are the actual structures from which physical reality is built. This is not a new idea. The Pythagoreans believed that numbers were the fundamental reality underlying all physical appearances. Galileo wrote that the book of nature is written in mathematical language. But the story of Riemann and Einstein gives this ancient intuition a modern precision. Here we see, with perfect clarity, a case where pure mathematical imagination produced exactly the language needed to describe a physical phenomenon that had not yet been discovered. Consider what this means for our understanding of the universe and our place in it. We are biological creatures, evolved from simpler forms through billions of years of natural selection. Inhabitants of a small planet orbiting an ordinary star in an unremarkable galaxy. And yet our minds, through mathematical reasoning alone, can discover truths about the fundamental structure of spacetime itself. We can sit in a room and, through pure thought, work out the equations that govern black holes billions of light years away. We can predict the existence of gravitational waves 90 years before we build the instruments to detect them. The fact that this is possible, that abstract mathematical reasoning can reveal deep truths about physical reality, suggests something profound about the relationship between consciousness and cosmos. Perhaps consciousness is not an accident, not a random byproduct of meaningless physical processes, but somehow embedded in the fundamental structure of the universe itself. Perhaps the mathematical structures we discover were always there, waiting to be found, and consciousness is the universe's way of discovering its own mathematical nature. Or perhaps the relationship runs deeper still. Perhaps what we call physical reality and what we call mathematical abstraction are two different aspects of the same underlying truth. Perhaps the universe is not described by mathematics, but is mathematics, an immense, evolving mathematical structure of which we are temporary patterns, brief arrangements of matter and energy, complex enough to contemplate their own mathematical foundations. These are questions that take us to the edge of what human thought can reach. Questions that have no definitive answers, but possess a beauty and depth that justifies the asking. Riemann worked at this edge throughout his short life, following mathematical ideas into territories that no human mind had explored before. He was guided not by practical considerations, but by aesthetic ones, by the sense that certain mathematical structures were more beautiful than others, more elegant, more complete. Einstein, too, was guided by aesthetic considerations when he struggled for 10 years to incorporate gravity into relativity. He was seeking not just a theory that worked, but a theory that was beautiful, mathematically elegant, conceptually unified, satisfying to the mind that contemplated it. When he finally found the right equations, he knew they were right, not just because they gave the correct answers, but because they possessed a kind of mathematical inevitability, an internal logic that seemed to compel belief. This aesthetic dimension of mathematical truth is something that working mathematicians and physicists understand intuitively, but find difficult to explain to others. Mathematical structures can be beautiful or ugly, elegant or clumsy, surprising or predictable, deep or shallow. These aesthetic judgments are not arbitrary. They correlate strongly with mathematical significance. The most beautiful mathematical ideas tend to be the most powerful, the most general, the most useful for understanding other parts of mathematics and physics. Riemann's geometry possesses this kind of mathematical beauty in abundance. It is general enough to describe any conceivable curved space, yet specific enough to make precise calculations. It unifies concepts that had previously seemed unrelated: the geometry of surfaces, the theory of differential equations, the physics of gravitation. It reveals deep connections between seemingly disparate parts of mathematics and physics. It is, in the opinion of those who understand it, one of the most beautiful mathematical structures ever created. And now, as you lie in the darkness listening to this story, you are surrounded by that geometry. The space around you is curved, warped by the mass of the Earth and the Sun and every object in the universe. The curvature is mostly imperceptible. Space is nearly flat on the scales of everyday experience, but it is real. It affects the flow of time, the path of light, the motion of objects. The GPS satellites orbiting overhead are programmed to account for it. The atomic clocks that keep global communications synchronized are adjusted for it. You are living inside Riemann's mathematical imagination, inside the curved spacetime that he described in that lecture hall in Göttingen. Every moment of your existence plays out according to the equations that relate the curvature of spacetime to the distribution of mass and energy. You are not separate from the mathematics. You are part of it, a temporary pattern in the universal mathematical structure, a localized concentration of energy complex enough to contemplate the equations that govern its own existence. This is perhaps the deepest source of wonder in Riemann's story. He created, through pure mathematical thought, a description of the universe so accurate that it governs your existence down to the smallest detail. The mathematical structures he explored in his mind correspond to the physical structures that define the space you inhabit. Between his mathematical imagination and your physical presence, across more than a century and a half, there is a connection as thought itself. Ideas do not need to be used to be true. Riemann's geometry was true in 1854, before Einstein was born, before the universe knew it needed describing. It was true in the sense that mathematical structures have their own existence, their own internal logic, their own in internal logic, their own internal. When Einstein finally needed that particular mathematical framework to describe curved spacetime, it was waiting for him, complete and ready to use. This suggests something profound about the nature of mathematical truth. Mathematical ideas exist independently of the human minds that discover them. They are not invented, but found, not created, but revealed. The mathematical landscape is as real as the physical landscape, and exploring it is a form of exploration, as genuine as mapping an unknown continent or charting the depths of the ocean. Some ideas arrive before their moment and wait. They sit in the literature, studied by specialists, admired by those who understand them, but not yet recognized as descriptions of physical reality. Riemann's geometry waited 60 years. Group theory, developed in the 19th century to study the symmetries of algebraic equations, waited until the 20th century to become the foundation of particle physics. Boolean algebra waited a century to become the basis of computer science. The mathematical structures needed to understand quantum mechanics were developed decades before quantum mechanics was discovered. The space around you right now is curved, shaped by the presence of matter and energy, according to equations that a shy, sick mathematician worked out in a German university town before your great-great-grandparents were born. That mathematician never knew his work would be used to describe the actual universe. He thought he was doing pure mathematics, following abstract ideas for the sheer intellectual pleasure of seeing where they led. He was, without knowing it, mapping the geometry of everything. Rest now. The equations will still be true in the morning. The space around you will still be curved. The mathematical structures that govern the universe will still be there, as beautiful and inevitable as they were when Riemann first discovered them. And you will still be part of them, a conscious pattern in the cosmic mathematics, a temporary arrangement of matter and energy capable of understanding the equations that describe its own existence. Sleep well. You are lying in curved space-time, surrounded by the geometry of a mathematician's dreams.